Good evening. Welcome to the Our Universe Revealed lecture series. My name is Deb Marr, and I'm a professor of ecology at Indiana University South Bend, and I'm serving as the moderator for this series. The Our Universe Revealed lecture series includes talks in science, music, and the arts. In other words, STEAM for everyone. We feature current research and creative work that's being done in our region, and it's an opportunity for us to be curious about ourselves, our world, and our universe. This is a partnership between Indiana University South Bend, the University of Notre Dame, and the St. Joseph County Public Library. Tonight, it is my pleasure to introduce Lauren Weiss. Lauren's passion for astronomy began early. She earned a bachelor's degree in astronomy from Harvard University, completed a master's degree in astronomy at the University of Cambridge, and then a Ph.D. in astronomy from the University of California at Berkeley. She served as a Trotter Fellow at the University of Montreal at the Institute of Research on Exoplanets. And then she served as a principal investigator of a NASA University of Hawaii Manoa program studying the diversity of planet interiors in Kepler's multi-planet systems. In Hawaii, she observed over 160 nights at the Keck Observatory as part of the California Planet Search Collaboration. Dr. Weiss joined the University of Notre Dame in 2021 and is an assistant professor in the Department of Physics and Astronomy. She has extraordinary research productivity, so an author on 91 research articles in peer-reviewed journals and over 4,000 citations. We have a privilege tonight to learn from someone who has a lifelong passion for deepening our understanding of planets beyond our solar system. And so with that, introduce Lauren.
Hello, everyone, and thank you for that lovely introduction, Deborah. Can you guys all hear me okay? All right, so first, I want to apologize for the weather. With a solar eclipse coming up, I wanted you guys to just have sunshine, clear weather, so that you can see what's going on in the sky. Of course, we have wind and rain instead. So fingers crossed that things will clear up wherever you happen to be for the eclipse in the next few days. All right. So with that, I'm here to tell you about eclipses in outer space, both this upcoming eclipse. I'm sure, who hasn't heard of the April 8th eclipse coming up? Good, you all have, at least from me. Right, so I'm going to tell you how I use eclipses of other stars to find their planets. And really the secret of this talk is it's the same physics, it's the same geometry of bodies moving in space. It just happens to be a lot farther away when it happens with planets around other stars. So let's start with the history of eclipses. So the word eclipse comes from the Greek eclipses. I'm not a Greek scholar, so I don't know if I'm pronouncing this ancient Greek correctly. This just means the sudden failure or abandonment of something. Very dramatic. And in astronomy, what this means is the sudden dimming of an object, the sudden diminishment in brightness. And we talk about two kinds of eclipses that we see here on Earth. One is the lunar eclipse, where the moon will darken and even turn a beautiful shade of red. And the other is the solar eclipse. That's the kind that we're about to experience in a few days. So what's the difference is the configuration of the sun, the earth, and the moon. Where these bodies are in space is what determines what kind of eclipse you get. So I hope you all have figured out by now that we're on a round Earth and it's orbiting around the sun. Hopefully that's not news to anybody. And we also have a moon, and that moon is orbiting around the Earth. So up here we've got a diagram on top with the sun illuminating the Earth, which then casts a shadow on the moon. That happens when the moon is in its full phase, and the type of eclipse that produces is shown up in the right. That's the lunar eclipse. Now that's That one you've probably seen before, but what we're going to see on April 8th is the other type of eclipse. What we have here is the sun, and then the moon gets right between the sun and the earth, and it casts a shadow. That shadow falls on the earth, and directly in the line of that shadow, you are able to see a solar eclipse. The moon is in its new phase for this kind of eclipse, and hopefully we will be treated to something like this. So, as you guys know, there's a big eclipse coming up. Important things to know are that here in South Bend, you can at most see a partial eclipse. A partial eclipse is what's shown in the upper right. The sun looks like a funny crescent phase. The reason for that is the moon is actually physically in front of the sun and blocking out light right there. However, not very far from us, if you go down to Bloomington, Indiana, perhaps at the IU Bloomington area or Indianapolis, you'll see something quite different, and honestly something more remarkable. So if I change your mind about one thing tonight, I hope it's to make the journey a few hours south of here so that you get to see this instead of that. So this is what we call a total solar eclipse, and it is what happens when the moon blocks out the entirety of the sun, diminishing brightness from the entire limb of the sun. So the path of totality of where you can see a total solar eclipse is going to travel through the United States, like so. You can see a few different cities pointed out, including Bloomington, Indiana, noted right there. My hometown of Rochester, New York is also on the path, and that's where I will be going tomorrow, actually. So I highly encourage you, if you haven't yet, take out your phone and scan this QR code. This is the NASA website of eclipse information. I know there's a lot of information online about the upcoming eclipse, right? You can read just about any news source and learn something, but why not learn from NASA itself? They're working hard. You're paying your wonderful taxpayer dollars so that they can tell you all sorts of great, accurate stuff about the eclipse, like how to view it safely. So I highly recommend checking that out. All right. So here's just another figure showing the path of totality with a few time stamps. You can see as time goes on, this shadow where the moon is completely blocking the sun is moving up and to the right. So speaking of safety, there's a second thing you get from this talk, right? The first one is go south for the eclipse. The second one is don't hurt yourself. So there is a time when you don't need eye protection, and that is during totality. That is, if you are in the path of the total solar eclipse, at that moment when everything is dark, you can take off your protective eyewear. That's kind of the point. Otherwise, you'll just be in the dark for 4 minutes. But at any other time, you need eye protection if you're looking at the sun. I know this because astronomers who used to not know it would look at the sun through their telescopes and they all went blind. So don't let that happen to you. Safe options include using a welder's glass of a sufficiently high rating, Mylar glasses, or special filters. Things that are not safe. Your favorite pair of sunglasses. They are not made for looking at the sun, they're made for just reducing a small amount of brightness. Regular glasses, transition lenses, no, don't look at the sun with those. Binoculars or a telescope, just because something is made for looking at astronomical objects doesn't mean you should point it at the sun unless it's properly filtered by someone who probably knows what they're doing. I wouldn't trust myself with a telescope with a filter. Just kidding, I would. Anyway, so you guys might remember the total solar eclipse of 2017. A couple days after that event, it came out in the news that this solar eclipse burned a crescent wound on a woman's retina. She was not wearing proper glasses. And this is actually the image published in a scientific paper showing you the burn on her retina. And then someone had traced out the shape they saw, and it's this vague crescent, because she was looking at a partially eclipsed sun. which will still damage your eyes. So second lesson of tonight is don't let that be you. So go to totality, always use proper protection. Okay, with those basics out of the way, let's talk a little bit about what eclipses look like. What's happening is the moon and sun are aligning with your physical location on the Earth. So this is an example of time-lapse photography that shows a total solar eclipse. The moment of totality is when the sun and the moon are aligned right here. But as you can see at other moments, they're not quite as well aligned. You also might wonder, well, why are they moving in the sky so much? That's because we're on a rotating ball. The Earth is turning. And so at the time of this eclipse, the sun is either rising or setting. I wasn't there, so I don't know. All right, but better than a time-lapse photograph is a video. So for now, we will travel to this beautiful land called Antarctica, which saw a total solar eclipse. So you see the sky darkens. And there's this sudden abandonment. Where did the sun go? It got very dark. And then it comes back. Totality, that moment of total darkness, is very short, only a few minutes. This is still part of that same video, but now a different time sequence, different angle. And also with different exposure settings, so you can still see the sun's corona, which is beautifully exposed there. Okay, so let's see how much you got out of the first part of this talk. This is the one and only quiz that you have to do. I know, we make my students do quizzes, so you guys are going to do one. All right, so we don't see a solar eclipse every year, right? This April 8th total solar eclipse is really special. Why is that? Is it because, one, the shadow of the moon only falls on a tiny fraction of the Earth? Two, only people on the equator can see a solar eclipse. Or three, the sun is much, much bigger than the moon. So go ahead, hold up whichever finger, 1, 2, or 3, you think corresponds to the correct answer. All right, we've got it mostly correct in the audience. The correct answer is number 1. The shadow of the moon is only falling on a tiny fraction of the Earth. 2 is not correct. We just saw a total solar eclipse in Antarctica, so that's clearly not right. 3 is a true statement. The sun is much bigger than the moon, but that's not why we don't see a total solar eclipse every year. It's because that shadow is only falling on a small part of Earth. So I'm going to drive that point home here by showing you some eclipses from outer space. So this is from the International Space Station looking down at Earth during the 2017 total solar eclipse. So it was a total solar eclipse for various people in North America. You can see this big, beautiful shadow here. That's the shadow of the moon falling on the Earth. And if we look closely, we can see that the shadow actually has some gradation to it. There's a very dark region called the umbra, where the shadow, it's a shadow where the sun is completely blocked. That's where you are seeing a total solar eclipse. The slightly lighter part here, the penumbra, is the shadow where the sun is only partially blocked by the moon. That's where you would see a partial solar eclipse. Incidentally, if you came here today with an umbrella, like I did, that comes from the same root for casting a shadow. All right, so let's take a look at an animation of a total solar eclipse as viewed from space. Right, so this is an animation, not real footage, but you can see the moon crossing in front of the sun. And even though the sun is much, much bigger than the moon is much, much closer to us than the sun is. And so from Earth or low Earth orbit, the moon can completely block the sun, although it doesn't do that for every single solar eclipse. So we've got a taste of what eclipses look like from space. And there's another phenomenon that I would like to share with you. This is actually, who here saw this? Yes. Yes. Okay, if you saw the transit of Venus, great. If you didn't, you have to live till like 21 something or other for the next one. So you've got to live a really long life if you want to see this from Earth again. So in addition to our moon, of course, which is beautiful, we live in this wonderful solar system that has many planets, including Venus. What's happening here is Venus is crossing between the sun and a very happy observer on Earth who's taking these beautiful time-lapse photographs. Right? This is Venus at various moments during its transits. And if you're wondering about that, that's not some dirt on the camera lens. Those are sunspots. Our sun is a place of wonderful magnetic activity and storms, and so there's plenty going on the sun with or without these eclipses and transits. But here, Venus, which has an orbit interior to that of the Earth, is crossing right between the Earth and the sun. Now, the word transit, you might know it from things like, I don't know, New Jersey Transit. I took that a while ago. It was bad. Right? Transit just means crossing from here to there. So eclipse, again, is sudden abandonment. Sudden dimming. Transit means crossing, but they're actually the same physical phenomenon. They're happening when one body in space goes in front of another. So this is the transit of Venus. So this is a planet in our own solar system transiting our own sun. And perhaps you can imagine if you were measuring the brightness of our sun during this transit, it would be a little bit dimmer when there's a planet blocking a small amount of light than when there's no planet in front of the sun at all. So we can use this fact to look at much more distant objects. This is a beautiful image of the Milky Way over a frozen landscape. We live in a galaxy with about 100 billion stars, including tens of thousands of them that we can study to look for planets. So this is just what we do. This is an animation that will show you what we do. So if you have some star and then a planet that transits or crosses between that star and your telescope, the brightness of that star dims very slightly while the planet is crossing in front of it. And when the planet finishes crossing the star returns to its full brightness. So we are able to look for that phenomenon, and we can actually measure something about the planets from these transits. The light that is blocked is the cross-sectional area of the planet. So from how much light is blocked, we can learn about the size of the planet. Now, Earth is 1/100th the diameter of the sun. And so if you were to place Earth in front of the sun in just such a transit configuration, you would only block 1/10,000th of the light from the sun. It's not very much. This is very hard to detect. Fortunately, like many things in nature, these transits happen to repeat, right? The planet goes around again and again and again. The time between these transit events is the orbital period of the planet. So detecting exoplanet transits from space has led to a revolution in our understanding of planets in the universe. This is a video put together by NASA in celebration of the 5,000th exoplanet that was discovered, an event which happened just a couple years ago. So it's telling you this story of our journey and showing you a map of the planets that we've found, some beautiful artistic impressions of what they might look like, and a few fun facts that we've found along the way. All right, so kudos to NASA for putting together that lovely video. If that went by a little quickly, I will walk you through some of the highlights of it now. So around the time that I left college, graduated from college, NASA launched a telescope called the Kepler Space Telescope, named after Johannes Kepler. You might remember him from Kepler's Laws, your primary school days. So this is an artist's rendition of the telescope. This was a mission that lasted for 4 years, and its primary goal was to detect Earth-like planets transiting in front of sun-like stars, which, as I told you, is just going to make a dip in the brightness of the star of 1 part in 10,000. So it had to be done from space, not Earth, because our atmosphere gets in the way. Kepler continuously stared at 150,000 stars for 4 years to accomplish this task, right? It's looking for these tiny little dips. What's neat is this is actually a part of the sky that you can see and identify, right? It's spring now, summer's just around the corner. Some of these constellations here, Cygnus the swan, Aquila the eagle, and Lyra the lyre, these form what's called the summer triangle. And this funny grid over here is representing the region that we stared at for 4 years looking for Earth-like planets. Let me show you a little bit of what we found with Kepler. This graph is showing you the brightness of a particular star over 600 days. And what you can see is, well, there's a lot going on the top. And that's related to systematics of the spacecraft and variability of the star. But when you get rid of all of that unwanted variability and look at just the brightness of the star over time, you'll see these drops that fall like rain. These are tiny dimmings of the star by just a few parts per thousand. These were the transits of 6 unique planets that happened periodically. Based on the repeated transits and the characteristic dimming and duration of each of these transits, they were identified as belonging to 6 unique planets. So on the left, what I'm showing is these characteristic dimmings from each of the planets and the real data that revealed those. And on the right is an artist's impression of this system. We don't ever actually get to see the planets because these stars are just too far away. But remember, because these planets are transiting the star or eclipsing the star, we get to learn about them and know how many planets there are and what their sizes are and what their orbits are. The orbits of the Kepler-11 system are remarkable. All of the 6 planets that are known, if you were to insert them into the solar system, they would fit within the orbit of Venus. And 5 out of the 6 planets would fit within the orbit of Mercury. Of course, in our own solar system, there are no planets interior to Mercury. For a while, scientists thought there was. They called it Vulcan. Then they learned about general relativity and realized that there was no Vulcan after all. It was just a behavior of objects in general relativity. All right, let's see. So what's really neat about the Kepler mission is over the 4 years that it ran, it found thousands of planets. This is a plot. It's showing you the sizes of the planets in units of Earth radii and the orbital periods of the planets. Helpfully, it did just tell you where we are. And as you can see, Kepler found thousands of planets, about the size of Earth to maybe about 10 times the size of Earth, most of them much closer to their stars than Earth is to the sun. But it did find a few that are encroaching on this region of Earth's orbit and Earth's size. Now, why is that special? Well, at Earth's orbit, we're at a very nice temperature. And if we don't keep warming up the Earth with global warming, it will hopefully remain a nice temperature here. It's a temperature where the surface of our planet can support liquid water, which I hear is essential for life. So we'd like planets that are at the right temperature for liquid water so that maybe they might be habitable or perhaps even inhabited. We'd also like to find planets that are small. Planets that are large are generally not rocky. Actually, something that I found in the course of my research is that planets should be smaller than about 1.5 times the size of Earth to be rocky. And we want them to be rocky so that that liquid water has a surface to actually pool on and drive chemistry. Okay, so what we want to know is how many Earth-like planets are out there. That was the point of the Kepler mission. We can count the planets that Kepler found, but it also didn't find a bunch of planets. Planets can be detected when they block the star and cause that characteristic dip from the transit. But it's also possible to miss planets if they don't transit, right? We're so lucky we're going to have just the right alignment for this total solar eclipse in a couple days. Well, we have to get really lucky for planets to have the right alignment to transit as well. Fortunately, we know geometry, so we can easily correct for all the planets that we've missed if we just assume that there's nothing special about our location or point of view within the galaxy. Hopefully that's a good assumption. A third scenario is that there's a planet that does happen to cross the star or transit, but we miss the transit because our data are too noisy. The variations in brightness are too great for us to identify that characteristic dip in the light. So putting all these different scenarios together, a few years ago, my colleagues came up with a remarkable result, which is that 1 in 5 stars hosts a Earth-sized planet in an Earth-like orbit. 1 in 5 stars has a planet that might be inhabitable. So when you look at the night sky with these 100 billion stars in our own galaxy and hundreds of billions of other galaxies that are out there, there are just so many worlds waiting to be discovered. I'm going to finish up by giving you a quick teaser about some of my recent research. So the other thing that we can do with these beautiful planets that eclipse and cast these shadows is look for patterns. We've found so many thousands of them. So a few years ago, I found that planets in the same system often have similar sizes and regular orbital spacing. That's exemplified by these systems in pink boxes. And we actually call these peas in a pod because they look just like little peas lined up in a pod. All right. So I'd like to finish by bringing together these ideas of this solar eclipse that's coming up and these beautiful transiting worlds we've been discovering. This is actually a video from quite a while ago. And what you're about to see is not an animation of a single system. This is actually, it's highly imaginative. The artist of this animation, who's also an astrophysicist, imagined what if all of the worlds we've discovered were orbiting a single star? What would that visually look like? And what you're about to see is, remember, this is not actually a physical representation. This is just a way to spark your imagination. And I think in particular, this video shows the remarkable effect of eclipses and transits. So let's watch this. Again, what you're seeing is not a real planetary system, but rather an imagining of what it would look like if all the exoplanets ever discovered orbited a single star. How wonderfully full of eclipses and transits such a place would be. We zoom out now and see that almost all of these planets that were discovered are well within the orbit of Mercury in our own solar system, and that we're still just beginning to probe the planets out at orbits like Venus, the inner edge of the habitable zone, and Earth, where we reside. So Earths are common, and yet we're still just beginning to find them. All right, I'd like to thank you for your attention and take any questions. Yes.
Oh, one of the things I was thinking about when you were showing your data and how you tried to find like the Goldilocks zone of where the planets can be distance-wise from the sun, I was thinking you must also take into account the relative heat of each sun
Yeah.
to find that particular Goldilocks zone.
That's right.
Okay.
Yeah, so there's multiple ways to calculate sort of distance. Right, and so what you really want is a temperature range. In theory, but for instance, Io is a moon of Jupiter. It's a volcanic moon that's resurfacing every 2,000 years or something. It's extremely hot on the surface. There's flowing magma, but it's out at the orbit of Jupiter. So the orbital distance of a body alone doesn't actually tell you the temperature. You can just get a guess about the temperature based on what radiation you're expecting from the sun. But there can be other sources of heat too. Yes?
What is the width of the shadow of the total eclipse at any given point?
Good question. No, it changes over time. The reason it changes over time is actually the moon does not have a circular orbit around Earth, but it has an elliptical orbit, slightly egg-shaped. So during some solar eclipses, the moon will be a little bit closer to Earth, and during some solar eclipses, the moon is a little bit farther from Earth. You might remember just this fall, we were supposed to have an annular solar eclipse, and then it was the day of a big Notre Dame home game, very exciting, and then it poured rain all day. So an annular eclipse is what happens when the moon is far enough from the Earth that it doesn't completely block out the sun. So the moon can be completely in front of the sun, but just like with, say, a transit of Venus or a transit of Mercury, it's not actually blocking out everything. There's a bright edge around the moon, an annulus, a ring. So that's why it's called an annular solar eclipse. We had one of those in the fall, but we didn't get to see it, at least not here in South Bend. A total solar eclipse can only happen when the moon completely blocks out the sun, and for that you need the angular size of the moon to be at least as large as the angular size of the sun. When the moon gets a little bit closer to Earth in its orbit, it has a slightly larger angular size, right? You bring something closer, it covers a bigger angle, and then that's when you can get a total solar eclipse. So, long answer, but the short version is know that there's not a fixed width, and it's going to change with each eclipse.
But would you say it's within an hour distance? Like, if you were to travel, I go to Bloomington, and then if I were to travel south, how long?
Oh, I mean, you should look at a map. And if you scanned the QR code from NASA, you can absolutely get like maps of totality and times too. Because the further you go from that line of totality, the shorter the totality will be. Yes?
Somewhere I recall somebody or something I read stating that our moon is the only moon in the solar system that allows us to have a total eclipse like the year.
Yes, I think that's correct.
One other question. So you mentioned there's a couple of other Earth-like planets, that exoplanets that have been discovered. So in terms of their Goldilocks zone, how much less intense would the sun be that it would have to orbit around to have that Goldilocks zone, since they're all inside the orbit of Mercury?
Right. There are plenty of stars in the galaxy. Actually, about half the stars in the galaxy are significantly smaller than and cooler than our own sun. Yeah, red dwarfs and also orange dwarfs too. And so actually a lot of the small planets that have been found in the Goldilocks so far are around these orange dwarfs that are just a little bit cooler and a little bit smaller than our sun.
So now, my understanding is that these dwarf stars would have a longer lifespan compared to our sun.
The cool stars, yeah. So these red dwarfs, yes, they are less massive. The lifetime of a star is related to the amount of fuel that it has divided by the rate at which it burns fuel. And it turns out that if you want to live a long time, you don't want to burn, what is it called? Burn fast, die young. That's what the big stars do. But the little stars do whatever the opposite is.
Would that give us a better opportunity of if we could go to these planets? Would we be better off going to one of these?
Probably not, because at least the M dwarfs, the very red stars, tend to have very active coronal mass ejections and solar flares that produce create a lot of ionized space particles, for which you would need to have a strong magnetic field on the planet to save you from that. We're just in the process of probing the atmospheres around some of these worlds around different types of stars. And exactly as you say, we're trying to understand, do they have atmospheres that would make them nice places to live? In the back.
Okay, so in reference to what you said, would our planet then be the only place where the moon lines up exactly in the circumference of the sun, or was there other eclipses that line up in that same diameter and circumference? Like in terms of it being, like you say, like Mars has eclipses, right? But its moons are shaped haphazardly. It's not like they're like it's not like just a perfect circumference.
Yeah, it's really, I think it's actually really striking that the angular size of our moon is almost exactly the same angular size as our sun, even though the sun is 100 times the size of Earth, and Earth is several times the diameter of the moon. It's really funny that the distances work out such that the angular size of the moon just barely blocks out the whole sun. And actually, in geological timescales, the moon is actually slowly spiraling away from the Earth. This is a tidal interaction between the Earth and the moon, same as the tides that cause our oceans to move around. So what's going to happen in the future as the moon spirals away from the Earth is eventually it'll be too far from us to cause total solar eclipses. So we're very lucky that we live at a time where we can see this.
Well, to add to that question, I was going to ask if there's any other places that they've detected that have the circumference matching I guess, the same way that our eclipses would be in our planet. Is there any other exoplanet that they've found?
Oh, exoplanets? We have not yet discovered exomoons, but that's in the works. We would like to. That sounds fun. We're trying.
Yeah. And then in terms of, you mentioned coronal mass ejections. Has there ever been like an EMP during a solar eclipse, and how would the, I guess if the moon was covering up the Earth during a solar storm, would that have any effect on the, I guess, the magnetic field of the Earth?
Yeah, so one phenomenon that we get during solar storms is aurorae. So actually just a few days ago, there was a massive coronal mass ejection that hit the Earth and caused beautiful aurorae in the southern hemisphere. Not sure if there were any in the northern hemisphere as well. It might just sort of depend on sort of where the blob hits Earth's magnetic field. So that's one major outcome. Another is that satellite communications can be disrupted. Charged particles, charged particles moving in space are electric currents, and they produce electromagnetic radiation, which can interfere with satellite communications.
In terms of if a solar storm happened during the...
During the eclipse?
Would the moon have some dispersal effect on the magnetic rays, or how would that work? Or once the eclipse was, I guess, out of that direction, would the...
Yeah, well, it actually takes a CME about a day to get from the sun to Earth. So if there's a CME that's just getting ejected from the sun during the total solar eclipse, that would look awesome. And actually, I think in one of my slides, I think I've got the 2017 eclipse in one of these, and you can really see, yeah, this one. You can really see the sun's corona. Corona means crown, same as coronavirus. That virus is named for having little crown-like spikes on it. So this sort of beautiful spiky pattern of this diffuse plasma, this is the corona of the sun. It's about 10 million degrees. It's actually one of the hottest parts of the exterior of the sun. And weirdly, though, if you actually put up a shield and went there, but were out of the way of the radiation, space there is actually very cold. So you could freeze, even though it's quite hot. It's complicated. But what you're seeing here is trace particles moving along magnetic field lines. So you could potentially see a coronal mass ejection, but what you would see wouldn't get to the Earth till a day later. And then the moon wouldn't be right in line with you and your spot on the Earth. You can actually see a prominence right here, this beautiful pink thing. Pink is from the chromosphere. Chrome is from the Greek word for color because of that characteristic pink color. So it's from a slightly deeper layer in the sun underneath the corona that's arching out because of a magnetic field. Let's see, take this one first.
All right, so you mentioned that a lot of the exoplanets that have been discovered are within the orbit of Mercury. And what I'm wondering is that something that is likely to be a feature of what exoplanets there actually are, or is it just a feature of what exoplanets we've been able to discover, given that the closer a planet is to its star, the more light it will block out?
Great, yeah. Excellent question. So the closer a planet is to its star, the more likely it is to have that eclipsing geometry, it turns out. If something's really far away from its star, you've got to get it really perfectly aligned to get that eclipse. But if it's closer, there's more wiggle room where you actually get an eclipse. So we're a lot better at finding planets that transit close to their stars. Something that we're working on right now is trying to understand how the inherent abundance of planets varies with location in the planetary system. One thing that we do know, based on these thousands of planets we've discovered within the equivalent orbit of Mercury, one thing we do know is that at least 1 in 2 stars has 1 or more planets within the orbit of Mercury. So already our sun, which has no planets interior to Mercury, we're in the 50% of stars that don't have planets there. And I didn't really have time to get into this, but something I've found in my research actually is that most of these other stars have not only 1 planet within the orbit of Mercury, but multiple planets in these beautiful patterns within the orbit of Mercury. Now, if our solar system had that, we would have found it. We're not very good always at finding what's out there, but we're pretty good at finding what's in here. So the fact that we don't have this beautiful pattern that's prevalent in so many other solar systems is curious. That said, we're still exploring the Earth-like regions in other planetary systems, and it seems like they are quite common, at least 1 in 5 stars having such a planet out there. But yeah, there's more work to be done for sure. There was a question in the middle here.
Oh, I had my hand raised. That was exactly the question I was going to ask, too.
Great minds think alike sometimes. Yes?
Is there a follow-on to Kepler? Is there another satellite out there now doing the same work?
Please give me like 25 million a year, plus whatever the costs are for actually building a Kepler replica, which we've done it once already, we can do it again, right? So I'd love to think that we could do another Kepler. I don't know if that's in the works at the moment, but we do have some other really exciting missions coming up, including the Nancy Grace Roman telescope, which actually has a much bigger field of view than Kepler, and it's going to be pointing weirdly toward the center of our galaxy. So we might find a bunch of transits that way, and they might be around a slightly different population of stars than what we've probed in the past. So keep your eyes and ears open. Yes?
I have a question about telescopes, but the ones down here on Earth, I understand why we put them out in space, but why do we put the telescopes in different places of Earth? You mentioned Iceland and Hawaii, and I read somewhere we're building one in Chile, but why those places? Why not?
Wonderful. Yeah, wonderful questions. So I was actually just fortunate in the past week to go to a conference in New Zealand, also called Aotearoa. It's in the southern hemisphere. So the sky that you see from the southern hemisphere is that way. We don't ever get to see that sky from here. I got to see the Southern Cross. I got to see the Large Magellanic Cloud. I got to see Alpha Centauri, the closest star system to the solar system. And I got to actually see both stars of that binary, Alpha Cent A and B, through a telescope. It was very cool. So we can see things that are different in the north and the south. That's one reason. Another is longitude. It is only night for about half the day, and then the other half of the day, we astronomers just sit around like drinking coffee and waiting, or teaching or whatever it is we're supposed to do. All right. So what's great is if you have telescopes all around the world, and you're like, hey, there's this thing I'm trying to study. I don't know exactly when it's going to happen. We'd like to monitor and look for it. That enables slightly better continuous monitoring from the ground. So there's actually a large taxpayer-funded program that does just that as well. Yes?
How is all this data being shared and collected? I assume, you just mentioned all these telescopes all over. Do you have any insights on that?
Yes, great question. Observatories are a little bit like medieval castles. Everyone kind of does their own thing. But what's great about public-funded observatories is making the data public is a huge deal. So actually, all of the NASA Kepler data is public. You can go online tonight, go on the Misulski Archive of Space Telescopes, and just download all the Kepler data. I don't recommend doing that unless you have a big hard drive. But you can download the data, you can play with it, and actually lots of astronomers have written beautiful tutorials. If you're a computer programmer, you can like just jump online, run through some of these tutorials, and within an hour you can be playing with real data from one of the best space missions that has ever flown to discover exoplanets. That said, other data is proprietary. Right? If I build my own fancy telescope in my backyard, I can do whatever I want with the data. So some telescopes are privately owned, some are publicly owned, and it depends. But I'd say overall, what we've been learning is there's just so much beautiful data out there in the universe, and our lives are so short and crowded and complicated that it's better to just share it, or err on the side of sharing. So more and more people have been reducing proprietary periods, making data public and accessible, and actually creating citizen science opportunities as well. So seriously, if you want, you can go home tonight and find real data to work with at whatever your level is. Yeah.
So why did they pick that particular patch of the sky for the Kepler mission?
Oh, fantastic question. So it is just, let's see this way. Okay. So apologies, this is sort of a low resolution image, but what you can still sort of make out here is going from the lower left to the upper right is a beautiful band. That's the Milky Way. That is the plane of our galaxy, a spiral galaxy that we live in. So this is quite crowded with many, many stars, but also dense gas and dust. It's very complicated to try to look at. There's just so much stuff going on. So the Kepler field was chosen to point just grazing along that galactic plane. You can see it's not quite pointing on the plane, but just off of it. A region of the sky that's still very dense with stars. There are actually millions of stars in the Kepler field, although only 150,000 of them were continuously monitored. So it was very carefully chosen to select many stars that we would be able to study without too much confusion, and also, astrophysically, stars that are quite similar to our sun in terms of their relationship to the galaxy as a whole. Yes?
Is there a minimum diameter? I'm kind of thinking, like, how do you distinguish between the planet and space junk?
Oh, space junk? Yeah, I'd love to be able to do space junk. That sounds really cool. I mean, so far the smallest stuff we've found, which was with Kepler, is like Mars-sized. Mars is definitely a planet and not space junk. But we would love to find smaller stuff. Actually, people who use infrared telescopes, including the beautiful new James Webb Space Telescope, are able to sense space dust, including tiny dust particles. Now, they don't see the individual dust particles, but they infer the density of the dust and its temperature and general properties from the light that they gather from it. So people are also studying dust in planetary systems. So we can do dust and we can do Mars, but we haven't figured out the in-between. Yeah.
Is there any value in like using James Webb or Hubble to look at a transit of an exoplanet?
Absolutely, absolutely. At this conference I was at in New Zealand, we had, I think, 3 separate sessions on new results from the James Webb Space Telescope. One of the main things that we are using James Webb to do is to study the atmospheric properties of these planets. We can measure their sizes. I taught you how to do that based on how much light they block. What I didn't teach you is how we measure their masses, which is also important because that tells us how well they're going to hold an atmosphere. Once we know those 2 pieces of information, we can look at light that has filtered through the planet's atmosphere, or try to do that. It's very hard. It's just like the transit of a planet, but it's the transit just of the outer atmosphere of the planet that we're trying to detect. It's very, very challenging. But James Webb is an enormous telescope, 6.5 meters, and it's in space. So it's in one of the best possible conditions for doing this kind of science.
Like its resolution is much
Yes.
Bigger than Kepler, I would imagine?
Yes, Kepler was a 1 meter aperture, whereas James Webb is 6.5 meters. And the big difference there is the light gathering power, which is going to be 6.5 squared times better, so about 50 times better.
But it has different uses than just look at one.
Yes, it doesn't just look for planets transiting, but we can point it at many different stars with planets when we know those planets are going to transit to study their atmospheres. I just learned that in some of these planets that are a bit bigger than Earth but smaller than Neptune, for a while we've been calling them mini Neptunes, but they're not what I just learned is they're not actually like mini Neptunes. Neptune has rock and ice, rock in the middle, and then some ice in a supercritical state, and then an envelope of hydrogen and helium. But these Neptune-like worlds, they're like Neptune in their sizes and masses, but they're much warmer than Neptune. They're inside the orbit of Mercury. They're getting roasted. And that changes their atmospheric chemistry. And what actually happens, and we've now seen this based on how light filters through their atmospheres with James Webb, is that these worlds actually have this, it's called miscible, or like mixed water and hydrogen envelope on the outside. So it's like a suspension of both water and hydrogen molecules all mixed together. Another example of a miscible fluid is vodka, alcohol and water mixed together. We have yet to find that atmosphere, though. And anyone else who hasn't asked a question yet? Yes?
In all your research and your studies, and like you find all these different exoplanets and so forth, do you ever reflect back on how unique our system really is? I mean, our sun is perfect. We have the right amount of planets that surrounds our planet. It's at the right distance, the type of star. I mean, all the other planets that we know have discovered, they're either too close or it's the wrong star. It's almost like a lottery. I mean, you're looking out there, it's like it gets bigger and bigger
Right.
each planet you find.
Yeah, so there are two competing philosophical principles here. You got me started on the big questions, right? The Copernican principle, which is we shouldn't actually be that special. We just happen to be observers in the universe. There shouldn't be something super special about where we are. But the anthropocentric principle is, well, hey, we actually are in the patch of the universe that became conscious of itself. That's amazing. And maybe some of the conditions here are a little bit different such that that happened. So those are two competing philosophical ideas. I think what will help resolve them is finding consciousness or life or, I don't know, whatever you consider meaningful. As we continue to search the cosmos, whether that's life on exoplanets or I actually think our best bet for finding life would be some of the icy moons in our own solar system. I mentioned Io earlier, which is volcanic and like way too sulfurous and hot for life. But other icy moons, Europa, a moon of Jupiter, and Enceladus, a moon of Saturn, they both have liquid water. They have salts. They have ammonia. They have organic molecules. They have the ingredients for life. So in some ways, you know, what we've got here on Earth is wonderful and special. But also there are other configurations that can give rise to some of the conditions that we think might be suitable for life. So we're still exploring. Can I take one more question?
Don't you think that it's more likely that maybe the universe was fine-tuned, especially our planet in its position, and the fact that all of these celestial bodies and the markers of seasons and everything are so closely aligned to just the way that our world is run?
No, I don't.
There'd be a creator that made all of this and that was able to, show his magnificence by, showing all of the, I guess the signs to just, I don't know, like that would be there for us to guide us in our life, in our daily life.
I mean, I think you can get personal guidance from that. That totally makes sense to me. But for me, I mean, I'm still looking, and we're still finding worlds that are approaching Earth-like. And no, I have not yet found an exoplanet that has soy chai lattes. like, which is my criteria for habitability, right? But
Who knows if there are other worlds that are inhabited, we just haven't discovered them, right?
right, but there's hundreds of billions of chances out there. So I'm certainly not ready to, to close the book and say, this is it, we're all there is. I think there's just so much out there to explore.
There could be other worlds out there that we're also fine-tuned in the same way that we're fine-tuned.
Yeah, so actually what's interesting is with some pretty different physical initial conditions, some of my colleagues have found other ways that life could have emerged. So what you describe, actually fine-tuning, is something that some of my colleagues have actually been exploring, and we're not as fine-tuned as you might think. So that's actually pretty exciting, including things like if the cross-sections of carbon were even a little bit different. It could be a problem in some ways, but also in other ways might actually make life much more prevalent than what we observe. So fine-tuning is an interesting problem, but really, until we get more examples and see what the variety is, we don't have a way to answer that question through the purview of science.
So I want to thank you for coming tonight. And And I just wanted to, so this is our last Our Universe Revealed lecture for this year. And in case you missed any of them, so this year, so in September, we dived into fungal pathogens, then thinking about eclipses, a discussion on the Nobel Prizes that were awarded this year. And then in December, we dove into music and creating music with understanding geometry. And then thinking about how bacteria communicate with each other. Then we got into origami. So again, geometry, but also folding patterns, what works, what doesn't. And then we explored a little bit of AI. And then of course tonight, we went out into the universe to see what's out there. So anyway, thank you so much for coming. If you missed any of these, you can go to universerevealed.nd.edu. You can see previous lectures. They've been videotaped by Steve Tope, and I'd like to thank him. He's been here. And you can sign up if you want to get notifications of things that are coming up, so what will come in fall of 2024. So thank you so much. And if you have any additional questions for Lauren, I'm sure she'd be happy to answer. Thanks.
Thank you.
Thank you.